Hello everybody, CRS here. This video is concerned with teaching you all the numerical problems that could arise in various chapters. We would be starting with electric charges and fields. That's the first chapter in our syllabus. These videos must help you solve any numerical that could appear in your exam. So keep yourself hooked to this series so that you will be able to ace all the numericals that would be present on your paper. All the theory questions are quite predictable, my dear friends. It's the numericals where we always get really hit hard. So let's make sure that we this time really excel in all of these numericals. Let's begin. So any numerical for that matter, when it comes in the board exam, marks are awarded for different steps. For writing the formula, there are marks. For substitution, there are marks. There are marks for simplification, writing the correct answer with the right unit. So if you can take care of all of these steps, which I will definitely be following in the problem solving process, I am sure there is nobody who is going to lose marks in the final exam. Let's begin with the video. Let's look at the first question. Here we go. Two charges, 10 nanocoulomb and 20 nanocoulomb, are placed 5 meter apart. Let us write this and visualize the situation. There are two charges. Q1, let us say, is 10 nanocoulomb and Q2 is 20 nanocoulomb. They are separated by a distance of 5 meter. The question says, well, Q1 and Q2 are known. Let's say that the distance between them is 5 meter and that is R. Using this, you can definitely find the force acting between the two charges. The force on each of these two charges is going to be equal as a result of Newton's third law. Let's look at what Coulomb's law. We are answering A part of the question. Coulomb's law states that F equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square mathematically. Now, when you are solving this question, you know Q1, you know Q2 and you know R. All that is remaining is just substitution. 1 by 4 pi epsilon naught is 9 into 10 to the power of 9. It can be written directly. Multiplied by Q1 into Q2, which is 10. Nano is 10 to the power of minus 9. Multiplied by Q2, that's 20 nano, 10 to the power of minus 9 once again. Divided by R square. R is 5. 5 square I shall write. You see, direct cancellations of 10 to the power of minus 9 automatically happen. Now we are going to simplify this further. Let me write on this part of the board. F, my dear friends, now becomes equal to 9 multiplied by 10 there is, and then there is 20 into 10 to the power of minus 9, whole thing divided by 25. So you see 5, 4 are 20 and 5, 5 are 25, and we have this getting cancelled as well. So F becomes equal to 9 into 2, 18, and 18 into 4 would be 72 into 10 to the power of minus 9 Newton. That is the answer for the first part of the question, the A part of the question. Let's look at the B part of the question, my dear friends. Let's look at the B part of the question. B part of the question says, the force between the two charges if the medium of relative permittivity 5 is introduced. Now you have this system of charges. Let's say you put them in a medium whose relative permittivity epsilon r is 5, then what would happen? Nothing much happens. The formula changes by a very little bit. Let's look at what the formula becomes. Let me call that Fm. Fm means the force between the two charges when they are kept in a medium. It becomes equal to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R square. In addition to this old formula, there is an epsilon r also in the denominator. That means whatever answer you got, 1 by 4 pi epsilon naught Q1 Q2 by R square, which is essentially 72 into 10 to the power of minus 9. You just have to divide it by epsilon r, which is 5. That would be the answer for Fm, and it turns out to be 14.4 into 10 to the power of minus 9 Newton. That is the force between the two charges in the medium. As simple as that. Let's look at the B part of the question is now answered. Let's look at the C part of the question. The change in the force between the charges. So whenever you're asked to calculate a change, the change in the force is always going to be the final force minus the initial force. The final force is Fm and the initial force is F. Let's substitute it here. Before you subtract, you just need to make sure that the powers of 10 in both the numbers are the same. Fortunately, that is the case in our situation, where 10 to the power of minus 9 and 10 to the power of minus 9, you can just directly go and subtract. You have 14.4 minus 72 into 10 to the power of minus 19 is what you have. This will turn out to be minus 57.6 into 10 to the power of minus 9 Newton. This is the change in force, my dear friends. So that's the change in force. I'll just put that in the box as well. Now going to the last part of the question. The last part of the question is force between the charges when they are brought in contact and then replaced in their initial positions. So let's try and understand this particular case. There are these two charges which are first brought in contact. If you have two tiny spheres, let's say, and they are conducting, this has q1 amount of charge and this is q2 amount of charge. When you bring them in contact, the total charge becomes q1 plus q2, and when you separate them, if their size is the same and the shape is the same, the charges get divided equally. So if this is q1 initially, q2 initially, it becomes q1 plus q2. When you put them together, separate them, and it becomes q1 plus q2 by 2. So in the next case, we are solving we are solving for question part D. q1 dash and q2 dash are the new charges. They are going to be equal because I told you that the total charge divides equally. And how do you do that? The total charge, my dear friends, is the sum of the charges in the first case, that would be q1 plus q2 divided by 2, that divides the charge equally. So initially the charges were q1 dash being equal to q2 dash equal to, initially this was 10 nanocoulomb plus 20 nanocoulomb, right, divided by 2 gives you q1 dash equal to q2 dash, giving you 15 nanocoulomb. That is the charge on each of those parts here. So we have the same two charges. This time is q1 dash and here it is q2 dash. The distance is still 5 meter. There is no difference between there is no difference there because the question says they are placed at their initial position. And that is the situation, my dear friends. The new force F dash becomes equal to 1 divided by 4 pi epsilon naught q1 dash multiplied by q2 dash divided by r square. All that is remaining is just substitution. 9 into 10 to the power of 9 multiplied by 15 into 10 to the power of minus 9, because this is also 15 into 10 to the power of minus 9, the q2 dash, you get q1 into q2, it's the same value, it gets squared, divided by r square, that's 25, my dear friends. You simplify this and the answer is going to be 81 into 10 to the power of minus 9 Newton, and that's the final answer for this problem. Well, just to get a whole preview about what this question was and how we have solved it, it's all there on the board. This is for you to just have a look at it, and any question like this in the exam is going to come for 5 marks. So I would like you to solve this independently and get your answers exactly the same as I. Let's go to the next. Let us look at the second question. Two charges, 10 nanocoulomb and 20 nanocoulomb, are placed at the corners of hypotenuse BC of a right angle triangle ABC of side AB equal to 3 meter, AC equal to 4 meter. Find the magnitude of force acting on corner A of the right angle triangle ABC if a charge of 2 nanocoulomb is placed at corner A. So let us imagine this triangle ABC to begin with. So that's our triangle ABC, by the way. Let me call this particular corner A and we will call this B, and then we will call that C. The charge that is placed at B, the question says is 10 nanocoulomb. We will call that, let's say, Q1, and the charge that is placed at C is 20 nanocoulomb. So we will call that Q2 if you like. And then there is a charge placed at A. We will call this charge Q3, right? We'll call that charge Q3. Yeah, of course, it's corner A. If you look at this, the two charges at B and A are positive charges, so they will repel one another. So the force that is acting on A due to B will be in this direction, and you can write that, you can just write that force F1. Let's call this force F1. Okay. And then there is a force of repulsion that is acting on A due to C. C is a positive charge. A is also a positive charge. So A will be pushed in this direction by C. So let me write that force here. I'll call that force F2. Right. We have depicted both magnitude as well as direction. So I'll put the sign, vector sign there. The resultant of these two forces is our answer, magnitude. Right. Magnitude is simply the length of the resultant force. We will calculate that. Let's name that vector F. The angle between F1 and F2 is something very simple. It's 90 degree, by the way. Let us also look at the second part of the question, the direction of resultant of force. Resultant force, the direction can be just stated by telling what is the angle that the resultant makes with one of the two forces. In this case, let's say it is F1. So we have to find the magnitude of F and alpha. Let's begin. For that, you will have to figure out what is F1 and F2 to begin with. So let's find out what is F1. F1, my dear friends, is the force between B and A. So you can just write that as 1 divided by 4 pi epsilon naught Q1 Q3 divided by the distance in here. The question says that distance is 3 meter and this distance is 4 meter. So I shall just write AB square. AB square. If you just do that, you will have 9 into 10 to the power of 9, because that's what is 1 by 4 pi epsilon naught. Q1 into Q3, which is 10 multiplied by, here it's a 2 nanocoulomb charge. It's a 2 nanocoulomb charge. So let us substitute it. This is 2 into 10, 20 nano is 10 power minus 9. You multiply both of them, it is going to be 10 to the power of minus 18 divided by, if it is a little shabby, then I shall write it again. It's 20 into 10 to the power of minus 18, by the way. Okay, so that's 20 into 10 to the power of minus 18 when you multiply both of them, Q1 and Q1 and Q3, divided by AB square. My dear friends, that becomes 9. This and this gets cancelled. So all you have is force F1. It's equal to 20 multiplied by 10 to the power of plus 9, and there is a minus 19. So it makes it 10 to the power of minus 9 Newton. This is the force F1. Similarly, you can find force F2. How do you find force F2? Force F2 has got a similar equation. It is 1 by 4 pi epsilon naught, which is common in all formulae. But in addition to that, you have the force between, F2 is a result of repulsion between A and C. And there is a 2 nanocoulomb and there is a 20 nanocoulomb. So you can just write that as Q2 multiplied by Q3 divided by the distance here is AC square, right? So this is 9 into 10 to the power of 9 once again, multiplied by Q2 is 20 nanocoulomb. Nano is 10 to the power of minus 9, multiplied by Q3, that's 2 into 10 to the power of minus 9, divided by AC square. AC square is 4 square, that's 16. And this answer, after cancelling these things out, you have 40 divided by 16, totally multiplied by 4, turns out to be 22.5 into 10 to the power of minus 9 Newton. This is F2. You've now figured out what is F1 and what is F2, how the job is done. Now you just have to calculate what is F. F, my friends, is the resultant of the two forces. In my videos, you can refer to the vectors videos of graphical method. There I've explained why the resultant force has this equation, which is equal to root of F1 square plus F2 square plus 2 times F1 F2 cos theta, theta being the angle between F1 and F2. This is the equation for the resultant force of two forces acting at an angle theta. In this case, my friends, theta is 90 degree. Theta is 90 degree in this case. So you simply substitute theta equal to 90, cos 90 becomes 0. This whole term goes to 0. All you have is root of F1 square plus F2 square. F1 square is 20 square there, and F2 square is 22.5 the whole square. You can just write 10 to the power of minus 9 simply outside, because it's the same there, it turns out to be 30.108 into 10 to the power of, I'm sorry, 30.103 into 10 to the power of minus 9 Newton. So that's what is the resultant force. This happens to be the resultant force. Well, when you know that this is the resultant force and you have to just calculate alpha, quite simple to calculate alpha. Let's find out what's alpha. Alpha can simply be written as tan alpha equal to sin theta by cos theta, the regular thing that you write, sin theta by cos theta, because sin by cos is tan. We have sin theta by cos theta being written with f2 here and f1 here. What is the logic? Why did I not write f1 sin theta divided by f2 plus f1 cos theta? Because please remember this logic. The formula has a structure. Sin and cos stick to that vector to which alpha does not stick to. So alpha sticks to f1. It does not stick to f2. So sin and cos get multiplied with that. That's the trick. Please remember it. So we have sin 90, theta is anyway 90. Sin 90, my dear friends, is 1. So you get f2 divided by cos 90 is 0. So you have f1. What is this ratio, by the way? This ratio happens to be f2 is 22.5 into 10 to the minus 9 divided by f1 was, if I remember correctly, yeah, it's 20. It's 20 into 10 to the power of minus 9. This turns out to be 1.125. That's tan alpha. If you just if you know how to use the Clark's table, there are quite a lot of videos. You can always refer to how to use the Clark's table. Once you know tan alpha, it's easy to find alpha. My dear friends, I'll just write that here. Alpha would simply be equal to tan inverse of 1.125, sorry, 1.125, and that angle turns out to be 48 degree 22 minutes. That's what is alpha. So we have answered both parts of the question. Let me just preview the question for you. So here is our question and the complete solution. The question asked us the magnitude of the force acting on corner A of the right angle triangle ABC if a charge of 2 nanocoulomb is placed. So I think we've answered this question. We've answered this question. A, here is the answer. That's the answer to that question. And then we also had to find the direction. Direction is simply the angle, and we have found that in this part. That's how you would answer this question in the exam if it occurs on the question paper. This problem is similar to the previous question, but here you have to calculate the electric field instead of the force. Let's find out how to do this. Two charges, 10 nanocoulomb and 20 nanocoulomb, are placed at the corners of hypotenuse BC of a right angle triangle, ABC of side AB equal to 3 meter and AC equal to 4 meter. Find the direction of resultant of electric intensity at corner A. We will also find the magnitude. Let's see how to go about it. It's the same triangle as in the previous case. Let me draw the triangle out. We'll name this triangle ABC like in the previous case. And here you have a 10 nanocoulomb charge, and here you have a 20 nanocoulomb charge, right? Right. And then at this place you have to find the electric field. How do you do that? Very simple. The electric field due to a positive charge at any given point. Now the point is A. We are talking about the electric field produced by the 10 nanocoulomb charge placed at B. Such a charge at any point produces an electric field away from itself. If this were a negative charge, the electric field produced by that point charge at A would be towards it. But now it's a positive charge, so it will at point A produce an electric field that's directed away from it. So that's why we'll simply call this electric field E1. Similarly, you have a 20 nanocoulomb charge there. It produces an electric field at point A too. So that electric field again is going to be in a direction away from that charge because it's a positive charge once again. So we have E2. This electric field E2 would have been in the direction of C if C were a negative charge. The angle between the two vectors is still 90 degree. The resultant vector is going to be in that direction. Let me call that E. Now all that we have to find is the magnitude of E1 and magnitude of E2, and then we will find the resultant electric field. So the electric field E1, my dear friends, is given by 1 by 4 pi epsilon naught q1 divided by r square, or in this case distance I would say is, let's say, ab square. Why? And what is q1? Q1 is 10 nanocoulomb charge and q2 is 20 nanocoulomb charge. When that is the case, the electric field produced by charge q1 at point A is E1, and it's given by this. Let's substitute. We have 1 divided by 4 pi epsilon naught, value being 9 into 10 to the power of 9 multiplied by q1, that's 10 nanocoulomb, divided by AB, my dear friends, the question says is 3 meter, whereas this is 4 meter. So AB square, I'm really sorry, forgot to write that AB square. So when you write an AB square, that's 3 square makes it 9. So this 9 and this 9 gets cancelled. So the answer you have is 10 Newton per coulomb. Now that is the SI unit of electric field. We have found E1. We also have to find E2. Let's try to find E2. E2, my dear friends, is also very similar. We have 1 divided by 4 pi epsilon naught Q2 divided by the distance. In this case happens to be AC square. Let's calculate that. E2 becomes equal to 9 into 10 to the power of 9. Q2 is 20 nano, is 10 to the power of minus 9, divided by 4 square is 16. If you just look at it, what does this become? This becomes 11.25 Newton per coulomb. That is the answer for E2 after simplification. Now we have E1 and we have E2. You can calculate the resultant electric field E. The resultant electric field E, my dear friends, becomes equal to root of E1 square plus E2 square plus 2 times E1 E2, sorry, 2 times E1 E2 cos theta, right? Now when that is the case, you can just substitute here, but you need to know that theta here in this equation is 90 degree, because that's the angle between E1 and E2. E1 and E2 make an angle of 90 degree, cos 90 is 0, so whole term, like in the previous case, vanishes. All we have is root of E1 square. E1 is 10 nanocoulomb, the whole square, plus E2 11.25 nanocoulomb, Newton per coulomb, the whole square. So the answer turns out to be 15.05 Newton per coulomb. That is the electric field. That is the electric field. That's the resultant electric field. You can go further and then calculate the angle alpha. Let's say we call that angle alpha, and let's find out what that angle alpha turns out to be. Tan alpha, my dear friends, tan alpha is, as I had told you, it's simply sine by cos, sine theta by cos theta. Alpha sticks to E1, so E2 will be multiplied with sine and cos, and then there is an E1 there. Let's substitute in here. We have sine 90, theta is 90 degree in this case. So theta sine 90 is 1, cos 90 is 0. All you will have is E2 divided by E1. E2 is, just look at this, E2 is 11.25, E2 is 11.25 and E1 is 10. The answer you get is 1.125. That's the answer for tan alpha. That's the answer for tan alpha. If you want what is alpha, alpha would be tan inverse of 1.125, and that turns out to be 48 degree 22 minutes, right? 48 degree 22 minutes. The angle is the same as in the previous case. The two questions were done so as to understand what is the difference between field and force. By now you must have understood that once you know the field at that place, just by knowing the field at that place, you keep a 2 nanocoulomb charge and you will get the force on it. That is exactly what is Q is equal, F is equal to Q into E. That's what is F is equal to Q into E. So with these two questions, you must have understood the difference between force and field and the relation between them. If you just compare both of them, the answers are the same. If you just take, in the previous case, charge equal to 2 nanocoulomb, you will certainly get the same answer as in the previous case. So the equation F equal to Q into E holds. So with this, let us look at the fifth question. 2 point charges 1 into 10 to the power of 8 minus 8 coulomb. So the first charge given to us is 1 into 10 to the power of minus 8 coulomb, and 4 into 10 to the power of minus 10, 4 into 10 to the power of minus 8 coulomb. So Q2 is 4 into 10 to the power of minus 8 coulomb, are 0.06 meter apart. Let's visualize this. We have charge number 1, that's Q1, and there is another charge here, let's say that is Q2. Here is the second charge. They are 0.06 meter apart, so the distance between them is 0.06, right? Meter is the distance between them. We need to find the location of the point at which the resultant electric field is zero. So we need to figure out where the electric field due to these two charges is going to be zero. So let's say that at some point here, the electric field is going to be zero. Why? Because there is going to be an electric field due to Q1. Q1 is a positive charge, because of which the electric field is going to be directed away from that point charge when it produces electric field at that point. Now, Q1 has produced an electric field E1, and Q2 also has produced an electric field at the same point, but that electric field is going to be away from that point charge because that's also positive. Had it been negative, then the direction of electric field would be at any point in the direction of the point charge. Now let me call that electric field E2, right? Now, when will you have the electric field zero? The electric field will be zero when these two electric fields, E1 and E2, are equal, because they are in opposite directions. They would cancel each other out. When they are equal, they will cancel and the electric field is going to become zero. Let's say that happens at a distance x, right? That happens at a distance x. Obviously, the rest of the distance becomes 0.06 minus x. That's the rest of the distance. Okay. Well, when that is the case, you can now figure out each electric field E1 and E2. E1, my dear friends, would become equal to 1 divided by 4 pi epsilon naught Q1 divided by the square of the distance to the point. Square of the distance is x square. And what is E2? E2 is 1 divided by 4 pi epsilon naught Q2 divided by 0.6 0.06 minus x the whole square. That's the electric field. Let's equate both of them because we want both of them to cancel. For them, it is mandatory that they are equal. E1 must be equal to E2 for you to have no electric field at that point, let me say P, right? At point P, if you should not have any electric field, this condition must be satisfied. Let me equate both of them by substituting 1 by 4 pi epsilon naught Q1 divided by x square becomes equal to 1 divided by 4 pi epsilon naught Q2 divided by 0.06 minus x the whole square. You have 1 by 4 pi epsilon naught getting cancelled. We have Q1. Substituting for Q1, it is 1 into 10 to the power of minus 8 divided by x square equal to Q2. Q2 is 4 into 10 to the power of minus 8 divided by 0.06 minus x the whole square. 10 power minus 8 and 10 power minus 8 gets cancelled. Let's take the root right away. If you take the root right away, I have 1 by x equal to 2 divided by 0.06 minus x. Cross multiply 0.06 minus x equal to 2x, by the way. 3x becomes equal to 0.06. X becomes equal to 0.02 meter. That is the answer for x. You can just call this point A and point B. So you can say measured from A. You can just say that measured from A, and that completes the answer to this question. It's an important question for the board exam. It's a very simple question, but if you make a mistake of expanding this as A minus B the whole square, that will consume a lot of time. Make sure you take the root right here. So let us look at the sixth question. A uniformly charged conducting sphere of radius 1.2 meter. The radius of the sphere turns out to be 1.2 meter, has surface charge density. Surface charge density is denoted by sigma, and that is 80 into 10 to the power of minus 6 coulomb per meter square. Find a part of the question, the charge on the sphere. So we have a sphere here, that's a sphere, right? And this sphere, my dear friends, is charged, the question says. So there is charge sitting on this sphere. The radius of the sphere has been given to you. The nature of the charge has not been provided in the question, so I shall assume that it is positive. This is 1.2 meter, right? We need to now calculate the charge. The charge, my dear friends, surface charge density essentially is defined as charge divided by area. So charge can be calculated as surface charge density multiplied by area. Area is 4 pi r square. So we have 4 pi r square. That's the surface area. All that you have to do now is just substitution. Let's do that. We have Q equal to sigma is given in the question. It is 80 into 10 to the power of minus 6 multiplied by 4 multiplied by 3.14, because that's what's pi, r square, that's 1.2 the whole square, and you simplify, you will get 1.45 into 10 to the power of minus 3 coulomb. That's the charge that is present on the sphere. Let us look at the B part of the question. The B part of the question says the electric field at a distance of 2 meter from the center of the sphere. So you need to calculate the distance from the center of the sphere, right? So let's say at this distance, the distance happens to be 2 meter, right? That's 2 meter, by the way. 2 meter. That's how far is the point. Because this point is outside, it behaves, the whole sphere behaves like a point charge. So the electric field at that place, my dear friends, becomes E equal to 1 divided by 4 pi epsilon naught Q divided by R square. So I shall just take small r in the first case here to be 2 meter. So let me substitute E equal to 9 into 10 to the power of 9 multiplied by Q. Q is just now calculated 1.45 into 10 to the power of 1.45 into 10 to the power of minus 3 divided by r square. R square is 2 square, that's 4, and this electric field in magnitude turns out to be 3.262 into 10 to the power of 6 Newton per coulomb. That is the value of electric field, and it's radially outward if it is positive and radially inward if it is negative charge. Let's look at the next question. The electric field at a distance of 1 meter. So now you are asking me to calculate the electric field at a distance of 1 meter. The actual radius is 1.2, but it's a conducting sphere. The question says it's a conducting sphere. If it's a conducting sphere, my friends, at any point inside the conductor, the electric field is 0. Because this is less than 2 meter, you would rather write that for the C part of the question, the answer would simply be 0, because R that you're talking about, which is 1 meter in this case, is less than the physical radius, hence electric field is going to be 0. Let's look at the D part of the question. The D part of the question asks you to calculate the total flux leaving the surface. Gauss's law is there for that. So you can basically, use Gauss's law, and then let's say that you draw a hypothetical surface around this sphere. So that's a hypothetical surface around this sphere. And you will see the total charge enclosed by it. The total charge enclosed by it, let's say, is Q. Q is the total charge enclosed, and if you just divide it by epsilon naught, you get the total flux through it. That's what is Gauss's law. So let's compute that. Phi equal to charge enclosed is 1.45 into 10 to the power of minus 3 divided by epsilon naught is 8.854 into 10 to the power of minus 12. That's the value of epsilon naught, by the way. So this answer turns out to be 1.6 into 10 to the power of 8 Newton meter square per coulomb. Newton meter square per coulomb, and that's your flux. So quite a simple question to go about. So this question involves application of Gauss's law. If you understand conductors well, you can apply these formulae and get the answer, but then these problems for you will be a good reference for preparing to write the board exams. So stick to these problems.